Hello. I wanted to share my own explanation or the way I see uh, binary numbers. So this is a short video or presentation on the concept between decimal and binary numbers and how binary numbers work. Binary is important because computers do talk in binary. Everything that the computers process it's on ones and zeros. It's only the two stages a computer or any electronic equipment knows. Um, Ones and zeros is basically a low signal or high signal, so it knows a on or off. So when the computer sees that sequence of cycles, high and low cycles, it starts interpreting that as zeros and ones. And that's how everything in the computer works. Every letter, every web page, every image, everything is digitized into a binary representation of that information. All that information is in binary. So when we talk about IP addresses on computers, it, even though we put them in decimal representation or we might put it in hexadecimal representation, a the bottom line is that computers are going to see uh, binary, especially when it comes to the switches and the routers. They're going to see either the hexadecimal numbers or the binary numbers. So all the IP addresses that are seen by routers that are layer three, those are represented. If it's IPv4, they're represented in a decimal representation, but the way the computers, the routers will see it is on a binary format. So that's why it's so important because once we do IP addressing and how to breaking up IP addresses, you need to know, if you know the binary format, it will make things a lot easier for you. So let me start with the decimal. How did the decimal work in our world? If I have a number, I'm gonna put it down here, that I said, 3,753. When I say that number, you make that on your mind and you already know what is 3,753. If you will have uh, paper money in your hand, right, you're expecting to see, well, let's imagine that we have $1,000 bills, three 1,000s, 700s, um, five tens, and three ones, right? Because in decimal numbers, we work on a ones column. Once you exhausted your numbers, you go to the 10th column. And when you exhaust those numbers, 10, 20, 30, 40, 50, 60, 80, 90, you go to the hundreds. And then on the hundreds, the same thing. Once you finish your sequence, you go to the thousands. So if I start counting, that I start counting 1, 2, 3, 4, and on my sequence like that, when I get to 9, what happens is that I jump to the next column. When I don't have more to do with single units, I have to jump to my tens column. And then now I said, okay, I have a 10 and 0 ones, right? So this column, the first one, after 9, resets to 0. Now, um, in mathematical representation, the ones, if it's a base 10 number, decimal, which is decimal is base 10, this column will be the 10 to the 0. This will be 10 to the 1, 10 to the 2, 10 to the 3. 10 to the 2 is 10 times 10, 100. 10 to the 3, it's 10 times 10 times 10, which is 1,000, right? So um, another thing to keep in mind is that in decimal, even though we don't put it there, but in front of these numbers, you always have a 0. It's because it means that you got 0 tens, right? And then if I go here to 10, you don't have hundreds and you don't have thousands. We don't write it down, but it is basically there. It's just that we don't put the zeros, right? And on 10 is the same thing. If I keep on counting on my sequence there, after 10, you go to 11 and so on till you get to 19. After 19, go to the next sequence, which says, okay, 9 cannot go any further. So when I add one more, it becomes 10. So this is a 0, and another 1 gets added to this column. So now I got 20. So this is how how decimal works, and we all know that. Now, when it comes to binary, when it comes to this side of binary, binary is based 2. This is base decimal is base 10. So you get 10 to the 0, 10 to the 1, 10 to the 2, and so on. So binary is base 2. So you get 2 to the 0, 2 to the 1, 2 to the 2, 2 to the third. If I make that into a decimal representation, this is a 1. 2 to the 1 is a 2. 2 to the 2 is a 4. 2 to the 3 is an 8. So in binary, you have only 2 stages. You either got 0 or you have 1. That's it, and I'm done. That's my only two numbers that I can play with. So when I start counting, I said, okay, I got 0. Now I got 1. And like in decimal, if I said, well, 1 plus 1, I have to then increase the next column, which before was a 0. I'm going to increase it to a 1, and this now goes to the 0 because it's my first state. So basically, if I'm adding binary numbers, 1 plus 1 is 1, 0. It's kind of odd to say it like that, but because when you see that, you might think of a 10, but it's not 10, it's 1, 0. And that's one thing that brings up, reminds me that when we talk about binary numbers, and you want to read a number, don't read like a 0, 0, 10, because 10 doesn't exist in binary. You had only ones and zeros, right? Here, we do say 3,753 because, yeah, we have thousands, we got hundreds, we got tens, and we got ones. In binary, we don't. We got ones or zeros. So if you read decimal, please, please, please treat 0010. This is not 00010. It's 0010. Anyway, so this is basically, this is in decimal. This will be my 0. This is my 1. And then this is basically a 2. And my next sequence here, okay, so if I want to keep on counting, so I'm keeping this one. So 0 now goes to 1 because my next one. And then what happens here? Well, if I do 1 plus 1 is 1, 0, but I already have a 1 here. So I need to increment on this one. So 1 plus 1 is 1, 0, right? So if 1 plus 1 is 1, 0, let me put the 0 here, and I carry the 1. So 1 plus 1 is 1, 0. So let me put the 0, and I carry the 1. And 0 plus 1 is a 1. So now this is my next sequence. 0011, 0100. Now, just like in decimal, I have my ones, my twos, my tens, and my thousands. In binary, you have your ones, your twos, fours, and eights. So if I take this into account, that this is my 4 bits there. Oh, by the way, when you get 4 bits like this, this is a 4-bit word. WORD. It's a 4-bit word in binaries. Usually you got 4 bits or 8-bit words. So it depends on, if you're using working on 4 bits or 8 bits. And then you can be working with 16-bit, 32 bits, 64 bits. It depends how big is the word. But in this one, it's only 4 bits. We're working on only 4 bits. So I can say, just like I do in decimal, here that I have a 2 and I have a 1. So that's basically like a decimal 3, right? And when I go to my next sequence, 1 0, I mean 0 1 0 0, that means that I have no 8s, I have 1 4, no 0, no 2s, no 1. So this is a decimal 4. So now I'm converting from my decimal side, this is my decimal side, my binary side. And like that, and continues like that. So what is 5? Well, the way also, and one way to see this, just like you see in the decimal, that you said how many hundreds, how many tens, how many ones, then you can see, you can do here the same thing. How many eights, how many fours, how many twos, how many ones. So if I'm counting and I need to do 5, what do I need to do 5 on if I have only these numbers available? Well, I need a 4 and I need a 1. And then I don't need any twos and any eights. I've seen some videos where they explain this kind of like with lights. Which lights do you have on? Because remember, binary is either on or off. So this is off, on, off, on. So if I see in a scoreboard and the 8 is shaded out, the 2 is shaded out. All I have is the light lit on 4 and the 1. Then when I add them together, then I get, oh yeah, that's a 5, and so on. So if I want to make up any number, let me say I'm going to go to 1, 0, 1, 0. Let's go 1, 0, 1, 0. So if I get this number 1, 0, 1, 0, what is this in decimal? Well, I do have the 8. I don't have a 4. I have a 2. That's 10. And I have 0 ones. So this is a decimal 10 in binary. And what's the next number? 11. Well, I keep my 10 and I'm adding a 1. That's 11. That is binary. That is binary. So like I said, anything that you see, just remember to try to look at what these ones and zeros means. It means the 0, I don't have it, that digit, on the ones that I do have it. So this here, I have no 8s. I do have a 4. I do have a 2, but I don't have a 1. So 4 plus 2 is 6. Now, let's make this bigger. When it comes to IP addresses, we use 8-bit words. Not just 4 bits like on this one, but do 8 bits. When you do 8 bits, what happens on the next bit is going to be not 8, but it's going to be 16. This will be 16 plus 16 is 32, and 64 and 128, sort of like this. So you got 1, 2, 4, 8, 16, 32, 64, and 128. So this is 4 plus 4 is an 8-bit word. Now remember that IP addresses, you have 4 sets of numbers, right? So this is set 1, set 2, set 3, and set 4, right? Um, at Miami-Dade College, I think my classroom um, a IP address, it was like a 147.70.40 that I don't remember exactly which one it was, but let's say that it was a I don't know, 65. That's how the decimal representation of my IP address goes like that. It's like that 147.70.40.65. So it is when you go in binary, it will be in a format like that: one number, the next number, the next number, and the next number. So if I have all zeros, that's a 0. And if I have 0, 0, that's a 0, dot, 0, 0. So this, it's 0, 0, 0, dot, 0. Oops. That's this IP address represented in binary is 0, 0, 0, 0, dot, 0, 0, 0, 0, dot, 0, 0, 0, dot, 0, 0, 0. And the routers definitely do read, all they see is this. That's how they're going to see your IP address, like a series of 8-bit words and 4 of them in a sequence. And that's going to understand that. Now, one of the interesting numbers in binary, it's 255. If I get all those numbers, I get the 1, 2, 4, 8, 16, 32, 64, and 128. I can use here the summation from, let me center this thing and mold it. Mold it, yeah. I can do the auto summation. So let me put here that this is the total. Right. If I do auto summation on Excel, I can do this and do auto sum. So when I add all of those together, what I get is what? 255. In computers, that's like a magic number because 255 means just all ones, right? Because it means that if I do 255, that 255, that 255, that 255, what it means is that I have once on all of this. Well, this is 255 to 55 dot all of this to 55. I say 255 because I have the 128, I have the 64, I have the 32, the 16, the 8, the 4, the 2, the 1, and all of this added together is 255, right? Um, so to convert a number to binary, I always, believe me, will do a little table with these numbers on top so I can see how to get the number um, into binary format. There's a whole bunch of little formulas that they show in the books and the internet and all that. That's fine how they do that. The way I do it is this way. Let me start with something simple. Uh, if my IP address at home is 10.10.100.32, that's my IP address at home. How can I represent this in binary? Well, this is simple because the first one is a 10. So this here is going to be a 10. How do I make up a 10 in binary? Well, I need the 8 and I need the 2, right? So that gives me 10. And everything else, so this is 10 in binary. Now, since I did 10, 10, I'm just going to cheat and go copy paste. And now I have 10, 10. Now, what about 100? Well, 100 is a little bit more complicated because, well, but definitely I'm not going to have the 160, 128 because it's just too high. So I'm going to have the 64. I do need a 64. And I do need the 64 because if I add 32, 16, 18, 4, 2, and 1, it's going to give me 60. It's going to give me 63. So I need the 64. Kind of like how can you make um, um 25 in decimal? If I want to do here 25, if I don't use tens, I have to use tens. I cannot say I have 21 singles because there's no such a thing. I mean, you have only 10 singles. When you're counting, you only have 10 to count with. So when you exhaust all of this, you need to jump to the next column and you have to grab a 10. And when you go to 19 and you go to 20, you don't have any more numbers here, so you have to grab a 10. Well, in binaries, it's the same thing. If I have a 64, if I need a number that's higher, I need to grab the higher number. So going back to this, so for 100, I don't have 128, but I do need the 64. And if I do 64, I say, do I need the 32 to make it into 100? See, from this one, I work from left to right. Um, so yes, I do need to that because this is 96. All right, perfect. So 96, I know I have a 4, right? So 96 plus 4 is 100. There you go. That's my 100 in binary. 0110 I'm reading like in two separate words, 0110 0100. So this all together, I have 64 and I have a 32 and I have a 4. So 96 plus 4 is 100. And then conveniently here, 32 is simple because all I need is a 32 and everything else is going to be 0. So when my computer, my router, sees this sequence of numbers, it knows that that's my machine. That's the IP address of my machine. It doesn't really know it that is a 1010 It just knows that it says 0000 1010 0000 1010 0110 0100 0010000. That's my computer. That's the IP address of my computer. And and that's it. So now, what about Miami-Dade? Okay, well, let's get the 147.70. It's going to be a little bit more complicated, but still, we can do it. 147. Okay, it's higher than 128, right? So we do need that 128. And believe me, remember that the highest number is going to be 255. So you'll never, ever see an IP address in IPv4 IP version 4 that is higher than 255, 255, 255, 255, unless you go back to the 80s and watch the movie The Net with Sandra Bullock, that they're looking for an IP address, and I think one of the numbers is like 350 something, and you're like, what? It just doesn't. There's no way. The highest number that you can get on an IP address, IPv4, in decimal representation is 255. There's nothing higher than 255. It doesn't exist, right? So um, going back to this, so for 147, okay, I got the 128. Do I need the 64? Well, that will make it 180 something. So I'll way past, so I don't need any of those, any 64s. What about the 32? Well, okay, so that will be 128 plus 32 is 160, right? 50 and 10 is 60. So nope, that's not going to work for me because it's going to give me more than 147. So most likely I would need a 16. So 128 plus 16 is 144, right? 128 plus 16, this plus 10 is 138, and 8 and 6 is 14. So it's 144. If you don't believe me, we can do here 128 plus 16. And I'm going to add this together. Yeah, it's 144. So once I get to this, it's like, oh, that's simple because now I need to, from 144, I need to go to 147. What I need to that, I need 3 more. Well, I need the 2, and I need the 1, and that will make a 147. 144 plus 2, 146, plus 147, and this is going to be 0. That's what I'm doing. It's just taking the numbers that I need in order to make that 147. What about the 70? Well, I don't need that. I do need the 64. I cannot use the 32 because it will give me like 96. It's way too high. It's a little too high. If I put the 16, that'll give me 70 plus 10 is 80. That's too high. So I don't need that. So I'll continue. 64 plus 8, that's 72. No, cannot use that. So 64 plus 4 is 68. I'm close. And then I need a 2. That will be 70. There you go. That 64 plus 4 is 68, plus 2 is 70. So this is 70 in binary. See how simple can we do that? Now 40, it's super easy to do because I have 32 plus 8 as 40. So 0, 0, 0, 0, 0, 0. 5 is another easy one because I got the 64 and I need a 1 to make it 65. So that's a 0, 0, 0. So this here is 147, 70, 40, 65. And that can bring me into, I can jump in here really quick with what's called the subnet mask. Subnet mask is in another class, but what routers use the subnet mask is to segregate networks and to see what's the if the IPs belong to a network or they don't belong to a network. So one of the common subnet mask is 255.255.255. That's 0. If I put that in here, let me grab this one, which is now easy and convenient. So this is 255, 255, 255, and 0 is basically this here. 0. So routers use subnet mask to identify networks. And what it does is that it uses what's called the subnet mask. Subnet mask to find patterns, right? So what subnet mask does is that it says, okay, when a subnet mask is usually a series of ones that goes from left to right, and it starts from most left, and it starts working towards the right to see where it stops. So what it does is that the ones and the zeros separate what is called the network number and the host number. This is throwing a little more besides binary, but it's just so you can see the importance of this thing. So that's how it identifies. So it says whatever matches what is in this series of ones in this portion of the IP address is what's going to be your network number, where you'll be what network you belong to. And this is what I call the don't cares, because I don't care what's in here. When it's 00000, I don't care what's in there. So that's what this means. It's 255, 255, 255, that's 0. So what the router does, he says, okay, this is the IP address, and this is the subnet mask. So in order to be on the same LAN, on the same network, part of a same group of hosts, the network part needs to match to say that you're part of the same network. So the router will take all these series of ones and says, okay, if I see any other IP address that has this pattern that matches this one, so let me copy that one. I could put it here. And if this one and this one matches exactly with a mask like this, because this is what you're telling me to look for, then they belong to the same network. So here it can be um, any number. Let me make it into a one. Oops, one um, 1 0 0. That makes sense, 0. So this here, since it's matching these patterns, exactly the same pattern, because I'm telling the router, look, these are all the bits I need to match. I know for sure that that'll be a 147.70 dot something, right? What is that something in this case? Well, this here. I got the 16 and I got the 4, so it'll be 16.20. So what this mask is doing is matching for any IP address that is 147.70 a 40 dot something. Why something? This X, because these are my don't cares. And if I change it to my home network, right? And I get, this is my IP address, and I'm using the same mask of 255, 255, 255, that's 0. Oh, I didn't get the last digit there. Yeah, it's not 0. And then this mask is 0, 0, 0. So these are my don't cares, right? Press the wrong key. So as long as this matches any 10.10.100.x with the subnet mask of 255.255.255.0, it will be part of my network, the same network. So that's what subnet mask would do. And like I say, it says zeros and ones, and like that. If I want to change this pattern, then I can, for the mask, I say if I want to include this bit as part of it, and this has to be, let's say a 0, not a don't care, then what about this? It's not going to be 255, 255, 255, that's 0 anymore. It's going to be 255, 255, 255, that 128. Why? Because I got a 1 here on a 128, and this will be my mask for whatever pattern I'm looking for. So it will be um, some computers that start with 10, 10, 100, that's something. Now, if you go a little further and you look into this, that means that if I have that my first bit has to be a 0, that means that, you know, if it has to match this pattern here, if my 128 is a 0, that means that I never go beyond 128. So all my IP addresses are going to be all the way to 127, because I will never get the 128. The 128 bit. So it's kind of like saying, okay, I'm going to give you some money, but I'm not going to give you thousands. I'm going to give you tens, the ones, the tens, and the hundreds. So when you go to that, and I said, I'm going to allow you to use the thousands, then the highest number you can do is 999, right? 999. That's the highest number you can have. It will never go to 1,000 because you're not allowed to use thousands. So in binary, the same thing. If I said, hey, I want you to keep this pattern and I don't want you to use this bit of the 128. You're always going to keep it at 0. So the highest number you can do will be 127, but that's on a different class on when we go more into IP addressing. But that's how binary works. It is important to know this here. This how you go from decimal to binary and how this 4-bit works. Because if you understand how this 4-bit word works, then when you go to IP addresses, it will make this thing a lot easier. IP addresses is just a set of 4 of 8-bit numbers. Okay, thank you for listening.